Hi everyone, my name is Mark Littlefield. I'm Director of System Products at Elma Electronics. And I and my colleagues are excited for the opportunity to introduce you to QMC, the new small form factor I/O mezzanine standard that we've been working on. We had hoped to have it actually done and in the can by today. It's not quite there. We have probably one more ballot round to clean up a few little things, but we're about this close to having it go out to ANSI. And so this is a good time for it to be introduced to the community. I'm going to introduce what it is, how it came to be, what its benefits are, and so on. My colleagues from Acromag and TEWS will be talking a little bit more about the actual technology that's going into the standard. So what is QMC? As I said, small form factor I/O mezzanine. Same kind of concept, and you'll hear this over and over again, same kind of concept as XMC, but in a much smaller package. It was designed, and I should be showing my show and tell here. So this is QMC, okay? It's really small form factor. It's designed to be modular and that you can have multiples of these in a system. It's designed to be scalable so that you can actually have double wide, triple wide, or quad wide versions of this. It's designed from the beginning to be rugged for military grade applications, but there's both an air cooled and a conduction cooled version as part of the standard. It's basically, it's really designed as an I/O mezzanine. So it has two connectors. It has the high-speed host side connector and also a high-speed I/O side or user connector. And that user I/O can either be directed to the front panel of a system or to the backplane. In addition, we chose a connector that has, it's very high-speed, high-performance connector. So we expect this as a standard to have legs. It's going to be around for a few years. So what is the inspiration for QMC? And I'm going to put this down because I don't want to be dropping things. The inspiration for QMC actually came out of VNX Plus. VNX Plus, or VITA 90, is a small form factor module. You see, quite small, but it's got a lot of the same capabilities as, say, an OpenVPX module might have. A very high-speed connector, data plane, control plane, expansion plane, blah, blah, blah. What we needed was an I/O expansion capability. And this module is too small for XMC, which is the typical go-to for mezzanine I/O expansion in OpenVPX. So what we did is in July of 2022, we started a study group in VITA, looking at the problem, gathering our requirements, doing our trade studies, trying to find a suitable small form factor mezzanine that we could use in VNX Plus. There are some out there. There's M.2 that's pretty well established, Mini PCI Express, the Acropacks, and a few others. But none of them really ticked all of the boxes. And so what we said is, let's start a new standard. Let's see what we can do that will tick all of the boxes that we want to tick. And so we finished our report in early 2023, kicked off a working group in March, and then since March we've been diligently trying to put this standard together. We had several objectives we wanted with this standard. Again, a mezzanine I/O that was small enough to fit inside that 19mm VNX Plus module. The host side connector needed to be, we needed both a host side connector and an I/O side connector, much like XMC is. We wanted high performance, at least PCI Express Gen 5. We wanted both air-cooled and conduction-cooled versions, and we wanted to be able to support military-grade rugged, so it had to stand up to the shock and vibration of those mil-grade applications. Secondary, but still pretty important, and this came out of the study, was that we wanted to be able to support other form factors. VNX Plus was kind of the driver, but we said, why limit to VNX Plus? So we said we wanted to be able to support at least VPX, VME, Compact PCI and PCI Express, and PCI Express Edge fingers. Now, surprisingly, those various form factors caused us a fair amount of work in making sure that what we came up with actually made sense for all of those form factors. And but I think it was worth the work, because what it's doing is it's going to enable a wider community of users for QMC. So, what role is QMC going to play in the market? As I said, it's basically doing the same thing that XMC does today. It's all about expansion. Adding I/O ports to a board or to a system, adding like additional computation, like FPGAs, GPUs, and in addition, like there's new AI ASICs available, and then storage. The thing is, it's just a much smaller package. This is a great illustration, and I think it was the Acromag folks that put this together to give you a sense of the scale of this package. And so, like I said, because we designed it from the beginning for rugged deployed applications, it's particularly well suited for that. So I'm going to wrap up by taking a look forward at what's coming up next. Now, we'll be talking a little bit about it in the presentation, but we do have a couple of DOT standards we're working on, some additional things to add to the infrastructure. But the core QMC is in the .0 standard. From here, what we want to make sure is that we've got good coverage in the other carrier standards. Things like VNX Plus, it's already captured in VITA 100. It's already nominally captured in. VITA 100 is still naturally in work, but it's already accounted for in VITA 100. We want to work with Greg and see if we can't get it into OpenVPX so that there's language to direct how to use that back panel I/O. And then we'll be talking with the PICMIG folks about how we can maybe incorporate it there as well. Interoperability between modules and carriers between different suppliers, naturally a concern for a new standard, not so much for this. We have done an incredible amount of work to ensure this. One thing I didn't mention is that because there's air-cooled and conduction-cooled versions, you can actually intermate an air-cooled QMC with a conduction-cooled carrier and vice versa. We ensured that. One rule we had going forward from the beginning, any QMC, any carrier. It's rugged by design, so it's good for lab, it's good for factory work, it's good for field deployment. However, because of its nature, because of its size and shape and what have you, it's small. Designers are going to have challenges in cooling this. There's going to be swap challenges that people are going to have to work a little bit to be able to meet, especially when you're learning the new technology, figuring out how best to use it. I think that people are going to be very innovative about cooling. I think that we're going to see some kind of interesting carrier designs, and we might start off in the low single digits, or maybe in the single digits or maybe low double digits in power consumption per slot. But I think we may see that go up over time as cooling designs take effect. But what's really exciting is that it's a high enough performance mezzanine that we'll start seeing applications in things like autonomous vehicles or edge computing or artificial intelligence. So with that, I'm going to pass over to my colleague Jan for diving into a little bit of the technical aspects of QMC.
Yeah, hello everybody. My name is Jan Zimmermann. I'm one of the two general managers at TEWS, together with Tim TEWS sitting right there. And I'm going to give you a short, brief technical overview about the VITA 93, also known as QMC. So first of all, we'll handle the physicals of the QMC, which is first of all the size. You can see here the single QMC with the sizes of 26 millimeters times 78.25 millimeters, which is, compared to XMC or PMC, really small. But I think with a shrinking IC package sizes, it's rather the perfect match. Also, the small size allows us to build single function modules. So if the carrier provides enough QMC sites, the system integrators can just add more and more functionality by just adding in one of these small cards. Also, the component height, the 4.7 millimeters, is well known from, for example, PMC and XMC, and has proven sufficient for most circuit designs. Then we have the connector that we use. It's actually capable of PCI Gen 6 with an up to X16 link. And another thing that is really important with QMC is that you may want to supervise the module's health via IPMI, and the QMC offers a great approach to be seamlessly integrated into managed systems. So that means it can be supervised and managed, but it does not have to. Then regarding the IOs, a single QMC comes with 40 IOs for the single. So for that module size, it's a really high IO density. But it's not only the IO density, it's also the IO speed that is special about it. And that especially allows its use with high-speed interfaces like, for example, Ethernet or Vision. Next up, I want to talk a little bit about the scalability that Mark already mentioned and why scalability is so important. You can see here we have a single, double, triple, and quad QMC, and it just scales up in size, which we've shown here. And the scalability allows us to use the QMC for a whole range of application, starting from simple I/O functionality on a single QMC up to highest complexity solutions with, for example, a quad QMC, when you, for example, use a Zinc UltraScale as a system on module. So the QMC designers can adjust the size of the QMC according to the functionality they need or want to implement. So on a quad UART design, for example, would fit perfectly on a single size QMC, while a large system on chip from example, AMD or Intel would definitely need more. And what does it need more? It does need more PCB area, more power, more connectivity, and also more I/O. And to address these demands, the QMC grow not only in size, but also in power, connectivity, bandwidth, and I/O count, as you can see on the slides. Also, the carriers can be populated with different combinations of the QMCs. So you can put a single QMC and a triple QMC on a 4-site or 4-slot carrier. And that is only limited by the PCIe link and the QMC sites on the carrier. Next up, we're going to talk about the host interface. You see the PCIe connector, so the host connector for the QMC is on the right, and it basically provides everything the QMC needs. First of all, you need power. It offers 3.3 volt for low power designs, and for high power designs, you would go for the 12 volts, and maybe also the 3.3 volts in parallel, if you want to save some space on the PCB for the onboard power supplies. And secondly, you need, of course, connectivity. And here the QMC's only interface standard is PCI Express. That may seem a little limiting at first, but actually it ensures interoperability, because this way, as Mark already said, every QMC will fit on every carrier. So also a single QMC, as shown in the previous slide, has the capability of using PCIe X4, and that scales up to PCIe X16 for a quad QMC. And then, as a third point, you may need to supervise your QMC via IPMI. And that is definitely possible with QMC, but we've dedicated the whole slide to that, so more about that later. And then, as a last thing for this slide, we have the JTAG interface. that allows thoroughly testing and factory programming of the QMC without wasting valuable PCB space for example, debug headers or an onboard test. Then we have the I/O connector and the I/O capabilities of the QMC. You see it's the same 80-pin connector type as you already saw with a host connector. And it provides 20 differential pairs per single QMC, which can also be used as 40 single-end I/O signals. And in addition to that, every I/O pin has its own ground pin, which is critical for the signal integrity of high-speed interfaces. Then the I/Os are grouped or organized in I/O pipes, 5 to be exact, as you can see here. This is an I/O pipe, and you have 5 on those on the connector. And they provide structure during design and usage of the QMC. Each I/O pipe consists out of 4 differential pairs and their individual grounds. So this means each I/O pipe has its own ground reference plane. And this allows us to support also isolated interfaces like, for example, 10G Ethernet. And it's really a large improvement for the system. And then once again, you see here the QMC's I/Os, they scale up to 160 per quad QMC. So regarding the cooling concept, we'll handle air-cooled and conduction-cooled real quick. What you can see here is an air-cooled QMC on an air-cooled carrier. And the mechanical fixation concept of a QMC follows a very simple rule, and that is that the carrier provides all mounting hardware. On the one hand, that means that the whole or complete mounting kit has to be provided by the carrier. This includes the screws, spacers, and on the other hand, that frees up the QMC designer from worrying too much about mechanical stuff, and also the integrator from compatibility issues. The standoffs you can see here, they're already pre-mounted on the QMC carrier, allowing us the easy mounting with the screws and the spacers of the QMC on the carrier. And the spacers, these ones, they're needed because to cover the place for a potential heatsink of the QMC, because the QMC specification allows us to put a conduction-cooled QMC module on an air-cooled carrier. Next up, we have the conduction-cooled version. Here's an example of how that may look like on the right, where you have the carrier on the bottom and the QMC on top, together with the Skyline heatsink, which is the only mechanical part that comes with the QMC and is usually pre-mounted. Then, once again, as with all the other QMCs, all the mounting hardware comes with a carrier. This includes spacers, screws, the thermal interface material that you see here, and of course the heatsink for the conduction-cooled carrier. So that means that the design of the cooling structure is 100% up to the carrier designer, as long as the mechanical envelopes are not violated. Also, this again ensures interoperability. One thing I want to mention in particular here is the thermal interface material here in red, because it extends over the whole QMC and provides a direct high-performance thermal interface to dissipate the QMC's heat. And that is really important and critical because of the amount of power dissipation you will need for QMCs, and also a great advantage over traditional mezzanine concepts. But more towards the power budget later. Last but not least, we have the stacking heights, where you all know traditional mezzanine cards come with a fixed stacking height, often forced by the fact that the mezzanine provides the mounting hardware, and that works really well for systems that match the fixed stacking height, but is a kind of a drawback for systems that would allow more stacking height. That's why QMC comes with a variable stacking height of 9, 11, 14, and 16 millimeters. The variable stacking height maximizes the component envelope of the carrier, for example, for CPUs or single board computers, resulting in additional space on the carrier. With that said, the QMC itself will always stay the same, and that means it will always fit onto every carrier independent of the stacking height of the carrier. And consistent with a policy that all the mounting hardware needs to be provided by the carrier manufacturer, also the carrier will define the stacking height of the QMC. And that's it from my side. Thanks a lot for your attention, and I'm going to hand over to Robert.
Okay, thank you very much, Jan. Okay, I'm Robert Greenfield from Acromag Incorporated. I'm the Director of Marketing and Business Development, and I'm going to talk a little bit more about the implementation aspects of putting the QMCs in various aspects. So one thing that Jan was mentioning a little bit before was the power budget. And we have multiple, on the host connector, we have multiple signal lines for the power. We have 4 for 3.3 volts and three lines for 12 volt power. With each pin rated for up to 0.6 amps, you're going to get a maximum power of up to almost 30 watts of thermal design power. Now, that was the one thing is that we wanted to do is make sure that you had plenty of power if you wanted to put a high-powered FPGA or GPU on it, you have plenty of power. Now, the one thing is, as we learned from the Spider-Man movies, that with great power, you've got great responsibility. That responsibility is going to go to the carrier manufacturer, but we gave them a lot of flexibility that they can do whatever they need to get that power off. And what we did was to standardize a lot of the aspects of the QMC module to assist the carrier or the system designer to get rid of that heat. So you'll notice that we have, we have here, there's the heat sink that's integrated and standardized on all of the QMC modules. So that's always the same. So it's a nice starting point for you for designing the carrier. The other thing that Jan mentioned is that we have variable stacking heights. So that simplifies the ability to put a fan underneath and blow air onto the QMC module to dissipate the heat. So a lot of work went into that to standardize that. And as you mentioned, all of the hardware comes from the carrier, so that makes sure that it'll all be standard and interoperable with different vendors. The other thing we mentioned is that for a lot of higher performance system design work, a lot of people want a intelligent platform management interface. Systems based on VPX, advanced TCA, and others are making more and more use of this IPMI interface. So we wanted to make sure that it was standardized, and so to maintain that interoperability. And the way we did that was that the information about the module type and also any sensors that are on the module and the data information, that could be pre-programmed into a EEPROM. And then the IPMC, or the controller that would be located on the carrier card, could then read that information over an I2C bus. We picked I2C because we know that it's pretty ubiquitous on all the EEPROMs. It's widely used, and we knew it would be around for a long time. So that simplifies being able to do a lot of monitoring the health status of your modules, such as the temperature, the voltage level, and a variety of other different information for that. So use cases. One of the biggest things is we wanted to make sure that this platform was extremely flexible. So we know that right now there's a wide variety of I/O functions that are available and implemented on mezzanine modules. Some of the popular things are analog I/O with A to D and D to A converters. You got digital I/O modules with discrete level monitoring and control, event counters and timers, but we also wanted to put capabilities for higher performance. Jan was mentioning with Ethernet, you could go up to 10 gigabit Ethernet. You've got serial communication, avionics like 1553, A-Ring 429, 818. We also support industrial protocols like CAN bus and also FireWire, SpaceWire, different things of this nature, high-speed USB interfaces. And with those high-speed connectors that we put on there, we also want to be able to support more powerful FPGAs and GPUs and video interfaces as well. So some of the applications that we've seen that are very common would be measurement and control applications. And then with the higher performance, you can get, with the FPGAs and the GPUs, you could get things like protocol conversion, you get image and video processing, sensor fusion, adaptive filtering, and what the hope is that with all the advances in artificial intelligence and machine learning, that those could also be implemented as well. We also wanted to make sure that even though it's capable of handling very high-end performance, it's also relatively affordable for some of the more basic things and when you're implementing in, say, an industrial or a commercial type application. So you can see that we're dealing with the very small size lends itself to a lot of autonomous vehicles, whether it's drones or ground vehicles. It's relatively inexpensive, so you could use it for, say, industrial manufacturing or transportation, different things like that. Also for scientific research with energy, linear accelerators, things of that nature, astronomical or astronomy type applications. So really what the advantage is that you can combine the modules that handle your sensor and actuator interfaces. You can combine those with industrial interfaces, such as your avionics or your CAN bus and things, and then also combine them with another module that has a GPU or an FPGA. So the possibilities are really endless of what you can do with a combination of these modules. So to give you an idea, like Mark mentioned in the beginning, is the inspiration for this was the VNX Plus. But we also wanted to make sure that there was a wider ecosystem of VPX and PCIe edge controller cards. We also have compact PCI serial with the Eurocard format for 3U and VPX. So we made sure that it would support all those different platforms. And in the table over on the right, you can see that you can mount the QMC modules either vertically or horizontally, and you can get a different combination. With some of the larger ones, like say on a 6U or a 6U Eurocard design or on a full-length PCI Edge carrier card, you could actually mix vertical and horizontal depending on what you want it to do. Then you've got custom carrier cards that you can design. We know that it's very popular in a lot of designs now to combine, say, a COM Express module for the CPU or NVIDIA Jetson GPU to provide the CPU. And then you can put in a very small form factor, in 79 by 79 millimeter space, you could put 3 QMC modules to provide a variety of I/O interfaces as well. So this is very, very versatile. Next. Okay, so here we got the reference slide to show you a comparison of the sizes. Now, the QMC module, roughly about the size of a US $quarter coin. What was it? It's basically about the same size as an M.2 module, but it has a lot more performance. You can see relative to the PMC or XMC module, and the inspiration from one of the first VITA mezzanine modules, the industry pack shown on the bottom below, which also had the 2 down-facing connectors and was widely used on a variety of different platforms. So one of the standard benchmarks right now is to put an XMC module on a VPX carrier card or single board computer. But one of the things with the size limitation is that you can only fit one on a 3U carrier card. However, with the QMC, you can see here we're using Acromag mini PCIe modules. And you can see that we've got 3 of those, but you actually, with the QMC module, you could actually stack 4 or 5 of them vertically. So you could get a mix of different functionality on that card. And then obviously with the future in mind, people want higher performance and they also want smaller size. So therefore you've got the VNX Plus carrier card, which is roughly about the size of a credit card. And you can actually put 2 modules, 2 QMC modules on that carrier card as well. Or if you wanted, you could put a double wide QMC on the VNX Plus. The next steps in the development of the standard, as Mark was mentioning, was the dot standards for VITA 93.1 and .2 is to have extension I/O modules and smart I/O modules that we can use to bring standardized breakout of the I/O to industry standard connectors. So what we have is the XIOM modules, the extension I/O. These modules over here, very small modules, and they have this connector bridges to the I/O connector on the QMC module. So you can use that for standardized front panel, extremely useful for PCI Edge cards, or you could also use it as an RTM module. And you can see we've got a variety of different connectors that can fit on a single wide, like we've got a SFP cage, we've got D-sub, micro D9s, we've got RJ45s, you got BNC and USBs. Then you could also go for double wides. You've got, was it a VHDCI connector as well with 68 pins or 88, and then even the triple wide where you could put 4 SFP cages on that. And then you have the Smart I/O module. So the difference here on the Smart I/O module is it interfaces to the host connector on the QMC module. And in the example we're showing here, you got an RJ45 and an Ethernet controller device on the SIOM module. So a lot of flexibility, but the big deal is that we standardize this. I like to say that it's kind of analogous to an FMC, whereas you have one single carrier card and then you have a variety of different extension modules that you can break out the I/O on industry standard connectors. Excuse me. So, oops. Okay, so that's it for some of the implementation aspects. And thank you for your attention. And we'll go to the panel.
Thank you, Robert. And I'll take that pointer from you. So why don't you guys come back up here, Mark and Jan. Come back up. So we're going to do questions in a group format here so that they can all take the heat together. And by the way, this is just some of the people are working on this. You said you had how many different sponsors on this standard?
We have 40 organizations.
40 different organizations that are helping work on this. So even within this room, there's other companies that are working on the QMC concept and everything here. So, there's a lot of stuff going on. So what we'd like to do is open it up to questions. We'll pass the mic around here between you guys. Who's got the mics on right now? Anybody? Nobody? Just Robert. Okay. Is there any questions? John, you can also ask questions too online there so we can hear you in the room. What's that? Yeah, I will. So John McHale has a question there.
So guys, I'm good. I don't need the mic, by the way.
No, we haven't really received that information.
Oh, you have your mic.
Oh.
It's on.
Oh, sorry. No, we've been really busy right now on developing the standard, so getting the message out. But we have had some inquiries about things like avionics and a variety of different I/O functionality. So we do look to expand it to a variety of different carrier cards to handle the defense applications.
I expect 1553 and CAN bus will be early implementations. Actually, and so the question is this has no kind of front panel I/O provision that it's designed to go back into the carrier. And the question was, is there any plans to add front panel I/O to this? And the short answer is no. And that's by design. And that's why we have the XIOM adapter that's going to be a part of 93.1. So the idea is you go into the carrier, and then the carrier provides that XIOM space to break out to industry standard connector. And that way you can put an XMC down onto a carrier, and the XMC has an accompanying XIOM that breaks that out into industry standard connectors. And then it's the carrier's responsibility to provide both connectors and that front panel access. That's how that's going to work. But this was really geared towards driving data to the backplane. That was the first priority, was getting that data out to the backplane. Does that answer your question? It does. Okay. So to that point, that's actually a very good point, and I was going to bring this up in the VITA meeting, but one of the things that I'd like to see as a follow-on to this is replacing that copper I/O connection with a blind mate coaxial or optical connection, so that you can plug a QMC down onto a carrier that's provisioned with those connectors and then go straight out to wherever it's going to go. That's one of the things that I always thought was missing from XMC. If you were bringing, like on an open VPX card, you're bringing in coaxial from your blind mate connector and you're trying to get that to an XMC. It's really awkward. You got to route it around and then to the front. It's really messy. Or to non-standardized connectors on the XMC. It's just awkward. If we could come up with a way to blind mate connect that, captured by standard, so that, again, any QMC on any carrier that's properly provisioned for coax or optical, I think that would be great. And so I guess this was a call out to connector folks. If you know how to do that, let's talk and let's see about standardizing that, because I'd love to see it.
Jerry, this is John Keller. Can you hear me?
Yeah, we can hear you.
Yep.
You can't hear me.
Yeah, we can hear you. We don't have enough microphones to go around, so we're kind of scrambling
Oh, that's
here.
fine. I have a question. This is John Keller. I have a question for Mark. You said that you expect 1553 and CAN bus to be early implementers. Would you extend that to something like ARINC 429? And as a follow-up question, what do you see as the future of this for commercial aviation?
So I see no reason why the ARINC standard couldn't be a part of this as well. I mean, and it's just that no one's asked me about that yet, so that's why I didn't mention it. But people have asked me about 1553 and CAN bus, and both from the supplier community as well as the integrator community.
Would there be any issues with certifying for aviation?
None that I'm aware of.
Okay.
I'd like to follow on to that question that was asked earlier about the I/O and stuff. It's a good chance to maybe ask about what about running to rear transition, rear panels and stuff like that, like an RTM type of thing, like we did with the PMCs.
So that was another real concern about or real reason why we wanted to do the XIOM. So the way that it would work with an RTM is that a supplier of the single board computer would provide an RTM, or rear transition module, with an XIOM site that corresponds with their QMC site. The QMC maps to the backplane through to the RTM, and then that just routes directly to the XIOM site, so that a QMC supplier would then supply the XIOM to break that out into industry standard connectors. That's always been a problem with XMC and PMC before that, is that when you make an RTM, what do you do with those signals that are coming to the RTM? You basically normally just break it out to a box connector and say, hey, integrator, you figure out how to connect to it. This way, you can actually buy the module that breaks it out to an industry standard connector, and you can use it straight off.
Sorry. So the question is about the power from a double wide QMC and how much power reasonably we can get out of the thing. As Mark said earlier in his presentation, I'd say early adapters are going to be like single digits. We expect up to 10. There still needs to be more of a mechanical study on that to really reinforce those numbers. But A lot of it's really going to be up to the carrier implementator to really be more clever and get that power out. So, but it's designed to scale up and be used for more powerful devices.
So I'll just add that, I mean, like I said in my presentation, it's early days. People are pretty clever, and I think that they're gonna solve a lot of these problems, but we can't really give you the numbers right now. We just don't have the data to support it. So yeah, so Bill was asking if, sorry? Oh yeah, I'll let you answer, but let me just repeat the question. So Bill was asking that this was kind of clearly leaning towards military type applications, but it seems that it's also ideal for industrial applications. And I'll let my colleagues from TEWS respond to that.
Sorry.
That's all right.
Yeah, so in the beginning of the working group, this was always in mind, yeah, it's rugged, but it's also aimed for industrial applications. So it's was always an aim to think about how can we do a cost-effective solution. So one special thing as well about the QMC is that you have a single design for air-cooled and conduction-cooled by just adding the Skyline heatsink. So in all the work we did, we always tried to make it cost effective as possible. So because then having the advantage of really limited time to market if you're a system integrator want to implement different IOs on your system. So we hope for an ecosystem of a lot of different IOs. So yeah, this should make it really cost effective to use just variable COTS modules available in the market to just get together from like a bright warehouse of different functionalities, whatever you need.
And to add to that, I think Robert already mentioned that besides military, we have all the other areas that you could implement that, like transportation, research, medical, and also, of course, industrial I/O.
So to elaborate a little bit more on the cooling, one of the unique things on this design is the carrier implementation. You can have different stacking heights that allows for different kind of airflow. So you can have a bigger stacking height, allow for a larger fin to let the airflow really go through. And that's also nice for different platforms, makes it more cost effective because depending on the height, you can change that. Yeah.
I'll add to that a little bit. So one thing that maybe is a subtlety that wasn't really clear from the presentation and is that there's basically two cooling problems. There's the cooling of the carrier, whatever electronics you have on the carrier, you've got to cool that. But there's also then the cooling of the QMC. And it's kind of two separate problems. With the conduction cooled, naturally, that's pretty clear. You've got metal, tin, metal, or perhaps things like heat pipes or things like that to actually move the heat around. In the air cooled, it's maybe a little bit more subtle. If your QMC is a relatively low power QMC, you probably just pop it on there and let natural air flow around it or fan blowed air around it. The carrier itself might actually even have a fan underneath it, and that's the stacking height's pretty important with regards to that. But what you could actually do is have a QMC with a Skyline heatsink that's then milled out to provide fins or pins or something like that, so that you can actually heatsink an air-cooled QMC on an air-cooled carrier, and that provides then a little bit extra cooling capability. That's not really captured in the standard, but you are free to do whatever you like as long as you don't exceed the mechanical envelopes that are defined by the standard.
I should say, and things like that are covered we have a design guide as well that kind of shows all those examples that we went through as we were studying about with the heat and the cooling. And for the industrial applications, as we showed in one of the slides, you have a PCI Edge carrier cards. So those will serve for non-military applications as well. So the design guide's a really good resource that will make available as well.
Yeah, we'll be releasing that in the next couple of months. That's not a controlled document, so it's not as rigorously, controlled like with balloting and what have you. But we'll release it when we feel it's ready. Yeah. So Yeah, I have to be honest, we didn't do anything in particular to address any concerns about space. We didn't have any members who were bringing up any particular concerns. Having said that, and what I know about working in the space environment, I don't think that there's anything in particular about QMC that makes it suitable or not suitable for space, other than maybe the connector and its rating for space type applications. And what I would say is at that point, to talk to Samtech, who is currently the provider of the connector, and see what's possible. So the question is this going to be a replacement for XMC? No, I don't think so. XMC is really well established. For the things that XMC does, it does very well. There's no sense in trying to reinvent the wheel at that point. But what I think it will happen is that we'll find kind of new and innovative ways to use a small mezzanine like this. I hearken back to some years ago in the old Die-4 days in early Curtis Wright. Single board computers would have a PMC site plus a little personality module to be able to add different kinds of capabilities to their VME cards. I have a feeling that people are going to start using these as personality modules, if you will, to add maybe a capability. Say you had a board that you didn't have space for an XMC, but you wanted to add a little bit of additional flexibility. This might be the way to do that.
Yeah, and I really think that especially for CPU vendors or SBC, or if you're going to do an SBC, it's great to have the additional QMC slot on there for like the modular and approach that QMC provides.
You talked about the design guide a little bit, and I know you guys took a different approach to this from most standards I'm familiar with. Usually somebody's got an existing thing and they bring it in and we turn it into a standard of some kind. But you guys didn't do that. Can you maybe go into just a little bit more detail on what you did there at the beginning? Because the first few months were quite interesting to go to some of the meetings there.
So yeah, we did not come to the table with a complete design, and that's why we did the study group. The real reason we did the study group ahead of time. We took a good 6-7 months in that study group to really kind of work out what it is that we wanted from this standard. What the boundaries were of what we wanted to achieve. We looked at a number of different connectors and settled on the best choice. That maybe is a little different than some standards where the standard is driven by the connector vendor itself. So this was really a truly industrial effort, industry-wide effort, in that it was multiple participating companies. The content of the document is provided from a number of different companies. It's not just one company writing the document, and we tried to be very even and even-handed in our handling of what went into the document, what didn't go into the document. It wasn't always easy. There was a lot of discussions that dragged on for sometimes weeks at a time, and sometimes it was a little discouraging. But in the end, I think everybody's pretty happy with the result. And personally, I would say that this is kind of a showcase of what true industry standards can come up with.
Give a shout out to Andy. He gave you a lot of things to talk about.
I'm sorry?
Give a shout out to Andy. He gave you guys a lot of
Andy.
Technobox.
Joe. Joe Norris. Joe Norris isn't here today, but Joe Norris from Technobox was a very early advocate for this, and he was voracious in coming up with ideas and exploring things, and then sometimes we accept, sometimes we reject, and the fact that we've got this design guide, a lot of the content of the design guide was stuff that was generated largely by Joe, but by other people too, that we just didn't. It wasn't appropriate to include in the standard document itself. So we took that material, and that's the basis of the design guide. And then we're kind of fleshing out from there to make it a little bit more complete and a little more readable.
How'd you zero on that size?
Yeah, I guess the biggest factor is that originally people came to us about looking at our Acromag, which is based on mini PCIe, which is 30 millimeters wide. But that wouldn't fit on the VNX Plus with a 19 millimeter connector. So we knew we needed to make it smaller. Some of the limiting factors is once we decided on the connector that we were going to use, that kind of gave us a little bit aspect. The 20, where we kind of went back and forth on the size, 26 millimeters wide seemed to work for a wide variety of different applications. Originally, it was going to be 80 millimeters long, like an M.2 connector, but then we found looking at things like VPX and VNX with the metalwork that it was going to conflict and there would be some problems with that. So we shaved it down to 78.25, and that's where we ended up, and we think that's highly flexible.
Right, as far as the width too, there's certain ICs looking at like 23 millimeters that giving 26 give us just enough to get the powerful ICs that we want on this thing as well.
So, go
Yeah.
ahead.
So I think, at least from our point of, yeah, so I think what we expect in the beginning is that the first modules we'll see in the markets will be single width. But of course, depending on the demand of the customers and applications, we will also see bigger sizes. So, but from the talks we had so far, yeah, we see single in the beginning because it, of course, also offers the highest flexibility.
Yeah, as I mentioned in my presentation part, it's definitely possible to mix and match. You can put a single QMC and a triple together if the carrier has 4 QMC sides. That is no problem at all. You're just limited by the PCIe link provided by the carrier in the end.
Yeah, the standard ensures that it's completely defined, that we have the interoperability between the carriers. So there are fixed positions for the mounting. We have the mechanical envelope. So as Mark mentioned earlier, so this allows to have like for conduction cooled boards like heat sinks, but also for air cooled, as long as you stay within this defined envelopes, like the QMC vendor can also add heat sinks on the air cooled. But with this concept of the carrier providing always the hardware, and as long as he stays in the defined mechanical concept, it should always be possible to add any QMC on any carrier.
Yeah, I would say that as far as the preparation of the standard, probably half of the work that we put into the standard was all around that question of whether we could actually achieve that any QMC on any carrier. And there was a lot of going back and forth with regards to the mechanicals about who's got responsibility for providing what and so on. I would say probably, easily 4 months work went into just that question. And if you take a look at the standard, you'll see it's nailed down tight. In reality, actually, I mean, the example that he showed, that Jan showed, had TIM, but you actually don't need to have TIM because it's all depends on what the carrier decides it needs. If the carrier decides that it needs TIM, the heat sink structure of the carrier provides room for the TIM. If it wants metal on metal, it structures it so that it's metal on metal. The QMC doesn't care.
Because the QMC is always the same size. It's that 4.7 millimeters thickness. No more, no less. Yeah. So, and it's a flat surface, so that gives you the building block to do the carrier heatsink.